Have you ever really thought about what it takes to build a thinking machine? I'm not talking about in a movie, but for real. Well, today, we're going to do just that. We're going on a journey, all the way from a pile of raw metal to a machine that can move, act, and, yeah, maybe even think.
Okay, so let's just dive right in. What does it actually take? Because this is so much more than just nuts and bolts. It's this incredible journey that weaves through materials science, computer logic, mechanical engineering, and of course, artificial intelligence. We're basically going to build a robot from the ground up, starting with its very skeleton.
So here's our game plan, our roadmap for the build. We'll start with the body, the physical form. Then we need to give it a language so it can understand instructions. After that, we'll get it moving and interacting with the world. And then comes the really fun part, giving it a mind of its own. And finally, we'll zoom out and look at what it actually means to live alongside these incredible machines.
First things first, before a robot can do, well, anything, it needs a body. And choosing what to build that body out of is probably the most critical first step you can take. This is where the fascinating field of materials science comes into play.
Materials science is really all about finding the perfect stuff for the job. And you gotta understand, this one choice dictates a robot's entire physical potential. It's a huge balancing act. Engineers have to weigh a material's internal structure against how it's made, all to get the exact properties they need. Do we need it to be strong, super light, flexible? The answers to these questions define the machine before a single line of code is ever written.
So when you get right down to it, there are three basic flavors to choose from. You've got your metals, like iron and aluminum, the strong, tough stuff. Then you have polymers, which we all know as plastics. They're lightweight, they're cheap. And finally, you have ceramics, which are incredibly hard and amazing with heat. Each one has its own list of pros and cons. And that right there brings us to the most crucial point. Every single material is a trade-off, no exceptions. Take steel. It's incredibly strong, right? But as you make it harder and harder by adding more carbon, it can actually get more brittle. On the flip side, polymers are light and cheap, but you know they're not going to have that same durability as steel. So choosing the right material for a robot's frame, or its joints, or its casing, it's just a constant game of balancing these properties.
All right, so we've got a body. Now what? We need to give it a nervous system, a way to receive and process instructions. We have to teach it a language. And, you guessed it, that language is code.
And really, that's the core of it all. A program isn't some kind of magic. It's just a super detailed to-do list written in a language that a machine can actually understand. Every single action, from the tiniest twitch of a little motor to some massively complex calculation, it all starts as a simple line of code. Now, this little flowchart here shows the fundamental building block of that language, logic. It's a dead simple program. It takes a student's score and asks a basic question. Is the score 35 or more? If the answer is yes, it does one thing. If the answer is no, it does something else. This simple if-then-else logic, well, that's the basis for every single decision a robot makes. Thousands, even millions of these simple decisions all nested together are what create really sophisticated behaviors. Okay, so we've got a body and we've got a language. Now it's time to put it all together. How do we translate those logical instructions into actual physical movement and action out in the real world?
This right here is the official, kind of technical definition of an industrial robot. But let's break it down, because the words really matter. Automatic means it runs by itself. Programmable means we can change what it does. And servo-controlled, that's the key. It means its movements are incredibly precise and constantly corrected by feedback. It's a multi-purpose manipulator that can move on multiple axes, which is exactly what allows it to do such complex and delicate work.
The real action happens at the end of the robot's arm. That's where you attach its hand. Now that could be a simple gripper, or it could be a super specialized tool. You can swap in a welder, a paint sprayer, a drill, you name it. This incredible versatility is what makes these industrial robots such powerful, world-changing tools in manufacturing.
So everything we talked about so far is a robot that just follows a pre-written program. It's very good at its to-do list. But what if we want it to learn, to adapt, to think for itself? This is where we make the leap from simple programming to the mind-bending world of artificial intelligence.
But here's the thing. The path to creating AI wasn't some straight, steady line of progress. Not at all. It's actually been this wild roller coaster of hype cycles, these big periods of huge optimism and tons of funding, followed by what they call AI winters, when progress would just stall and all the money would dry up. This history just goes to show you how incredibly, profoundly difficult it is to try and replicate something like human intelligence inside a machine.
And that gets to a crucial point. The entire approach to AI has radically shifted. Old AI, the first attempt, tried to program intelligence with these rigid step-by-step rules, like a gigantic, impossibly complex flowchart. And it mostly failed. Why? Because the real world is messy. It's unpredictable. You just can't write a rule for every single possibility. Modern AI takes a totally different path. It learns from massive amounts of data, finding patterns all on its own, a lot like how our own brains learn from experience.
At the very heart of this modern approach is something called the artificial neural network. It's a computer system that's literally designed to mimic the human brain, with all these interconnected digital neurons. By churning through just insane amounts of data, these networks can learn to recognize images, understand language, and control a robot's movements. This ability to learn instead of being explicitly programmed, well, that's the game-changing technology that's driving the entire AI boom we're seeing right now.
So, we've done it. We've built our robot. It's got a body, it's got a language, it can act, and it even has a mind that can learn. And this brings us right into the present day, and it raises a whole new and much more complicated set of questions. How do we work alongside these machines, and what does their very existence mean for our future?
You know, one of the most exciting developments is augmented reality, or AR. Now, this isn't about replacing the real world with a virtual one. It's about enhancing it. Just imagine a mechanic looking at an engine and seeing digital labels and instructions floating right on top of the real parts. It's not science fiction. Companies are already using this on assembly lines to help workers, creating this totally seamless interface between human and machine. And now for the big one, the question that's on everybody's mind. As these machines get more and more capable, we have to ask a really fundamental question. Is this technology ultimately a promise for humanity, or is it a peril? On one side of that debate, you have brilliant thinkers like the late Stephen Hawking. He warned that a superintelligent AI could, one day, slip from our control and the consequences could be devastating. It's a view that takes the potential threat of our own creation to its ultimate and frankly very sobering conclusion.
But on the other side, you have the optimists, like Mark Zuckerberg. They see AI as this incredible tool that will help us solve some of our biggest, most intractable problems. Everything from curing diseases to making transportation totally safe. This view frames AI not as a threat, but as one of humanity's greatest possible achievements.
And then, there's a third, more pragmatic view. Experts like roboticist Rodney Brooks suggest that the sci-fi nightmare of a rogue AI is probably still really, really far in the future. The much more immediate challenges, they argue, are the things we're actually dealing with today. AI systems that reflect our own human biases, and the very real economic impact of automating jobs.
And that leaves us with this final, really profound thought from the science fiction author Philip K. Dick. Because maybe the biggest impact of building these intelligent machines won't be about what they do for us or what they do to us. Maybe, just maybe, it'll be about how they force us to completely reconsider what it even means to be human in the first place.